So what we've done before this section, which is part 3 of 7.2, is we found area between two curves when we did the top function minus the bottom function. So that would be the integral from a to b of the top function minus the bottom function. That's how you find the area. And then we took that region, sorry about that, and then we took that region and we revolved it around an axis. So then that was finding the volume. So we did pi times, and this one is washer method because we have a gap here. So we're going to have the top function squared minus the bottom function squared separately. We also did situations like this where we had our region touching the axis that we're revolving around. Here, let me do a different example than that. Let's say we had two functions like this. So this line is f of g of x and that line's f of x, and we're revolving around this. So that is integral from a to b of the top function minus the bottom function, the whole thing squared, because our region is laying right on the axis so we're revolving around. And then we had other function where if we had a function, just one function like this, which technically is f of x minus g of x, we would have pi times the integral of just f of x itself squared. So those are the situations we've had before. And now what we're going to do is find the volume of something that's not being revolved. So let's say we have some kind of shape, like a square prism. If I want to find the volume of a square prism, I need the area of the base and then times the height. Okay, what we're going to do is use the formula for area of the base, and then our height is going to be a very, very tiny height. So we're going to have the area of the base and then times the height of many, many different little rectangular prisms. So all of these little tiny heights, and we're going to add all of them up. So it's the accumulation function. We're going to find the area of the base, and then this is going to be like the dx, the width, and that we're going to sum up. So we're going to have the area of the base, and then with respect to x is going to be the height. So we just are going to integrate, because integrating means adding up the volumes of all these little tiny shapes, and the area of the base is the function that we're going to integrate. So let's get into that. 7.2 part 3, the volume of solids with known cross sections. So if we cut up this region, we've got this weird looking region here, we cut it up into a little rectangle. We know the area of a rectangle, and then we're going to multiply the area of the rectangle times this width, which is little teeny distance, delta y or dy. That will give us the volume. The area of the base times the height or width will give us the volume of that one shape, and then we're going to add up a whole bunch of them. So we're going to imagine cutting this up into an infinite number of those rectangular prism shaped things, and they aren't all the same size. In fact, if they get down here, they're really tiny. So we're going to add up the volumes of all of those, and the volume is the area of the shape times dy. This one has cross sections that are perpendicular to the y-axis, and you can see how this is a three-dimensional picture. So the x-axis is here and the y-axis is here. Here the x-axis is here, the y-axis is here. These cross sections are perpendicular to the x-axis. So we're going to integrate with respect to x, and this a and b are going to be x values, and these c and d are y values. So we're not doing any revolving, we're just going to take the area of whatever cross section. So if you're slicing a loaf of bread, whatever shape that is that you slice, if you slice this region, then that is the area formula that we're going to use. And this area formula is based on the equation. So if we have the equation for this, you can see that this side here is this equation. And then if we have the equation for this side here is this equation. So we're going to take this equation times this equation. And that will be the area because we have a rectangle. Or if we have a circle, then we're going to take the area of the circle here. Or if we have a triangle, we're going to do 1/2 base times height to get the area of the triangle. Or the equation for an equilateral triangle, whatever area equations we need. So the only way that these types of volumes with known cross sections are going to have a pi in them is when the cross section itself is a circle. Remember back here, we didn't have a pi here because we were just finding area. Here we were finding volume. These were all volumes and they only had pi in them because we were revolving something around an axis. So that was area of the shape revolved around. So we had to do pi r squared. That we always had circles in these situations here because we were revolving. We won't always have circles here, so we won't have a pi. But this formula has to be a volume or an area formula. So let's look at this. If we have the equation f of x equals the square root of x. So here's our square root function. This is our x-axis and this is the y-axis. X equals 4 is this line right here. X equals 4. And y equals 0 is this line. So the equation square root of x equals 4 and y equals 0 are the boundaries of a figure with semicircular cross sections. So the base of the shape is bounded by this region, but then in that region we're going to have semicircles coming out of it. So it's going to stick up into semicircles. If they had said rectangular cross sections, then instead of semicircles we would have rectangles sticking up out of this. So they would go like that, and it would tell us like the height of the rectangle or something. Or if it said triangular cross sections, so our triangles would come up and stick up out of this region and would follow whatever shape we have going on here. So sometimes it's hard to picture the idea of what this region's going to look like. So here's an example of what this one looks like. It's got semicircular cross sections, but the base of that semicircle, the diameter part, is right on this region right here. To find the volume of the solid formed, find the area of each slice of the figure using the equation and the formula for the area of the shape of the cross section, and then you integrate. So we have to think about the base here is the diameter of a circle, and the equation of the diameter would be the distance from y equals 0 to the square root of x, which is the square root of x. The shape we're looking at, our cross sections, are semicircles. So the area of a semicircle is 1/2 pi r squared. That's where you start, is you figure out the area formula for the type of cross section you have. And then you fill into this equation something that's based on your region. So the diameter of the cross section is square root of x. So the radius, which is half of it, must be square root of x over 2. We're going to put that in for r, into the pi r squared over 2. So in there for r. So we're going to have pi r squared over 2. And we're going to integrate that from 0 to 4. The only reason we have pi involved here and the squaring is because our equation for area has a pi r squared, because the semicircle is the cross section. So this right here will always just be the area of the cross section, and the equation for the area of the cross section will always be based on some equations that we have in our boundaries. Okay, and then we integrate it. So let's set up another one. Find the volume of the solid whose base is bounded by the graphs of f of x, which is 1 minus x over 2. So f of x equals 1 minus x over 2. And g of x, which is negative 1 plus x over 2. So these two straight lines. So this is regular, y-axis going vertical, x-axis going horizontal, and x equals 0 is the other boundary. So the base of our shape is a triangle. And it says, oh, it doesn't say find the volume of solids, base is bounded by, and it should say with semicircular, or with triangular cross sections. And it should say equilateral triangular cross sections. Again, my examples aren't very detailed, obviously. So, we need the formula for area of an equilateral triangle. You always start with the area formula. And the area for an equilateral triangle is the square root of 3 over 2 s squared. Square root of 3 over 4. And the 4 is not in the square root. Sorry about that. So the area of an equilateral triangle is the square root of 3 over 4 and then s squared. And s is the length of a side. So that's the area of one triangle. The width of our triangles are delta x. So the volume of one triangle would be the square root of 3 over 4 s squared with respect to x. So that's area times the width of one rectangle, or one triangle, I mean. And we want to add up an infinite number of them. So we're going to integrate that, and that will give us volume. Now we've got to figure out something to use for s, and we've got to find our limits of integration. Oh, and we didn't even talk about if we're doing this with respect to x. But notice our representative rectangle is perpendicular to the x-axis. So we are integrating with respect to x. So now we need the distance from here to here. Top minus bottom again. So s, the length of one side of our triangle, will be the top function, 1 minus x over 2, minus the bottom function, which is negative 1 plus x over 2. So if you simplify that, 1 minus x over 2 plus 1 minus x over 2, that'll give us 2 minus 2x's over 2, which cancels, and we'll have 2 minus x for the length of one side. So our volume equation is going to be the square root of 3 over 4 times 2 minus x squared dx. Now what are my limits of integration? They have to be x values. So here to here, 0 to 2. And then we're going to integrate that. U can be the inside, 2 minus x. Du dx is negative 1, so dx equals negative du. Pull out the constant. So we have u squared. This is going to be negative du, so I'm also going to pull out that negative there. That's why I wrote that negative there. And our limits of integration would change, but I'm going to keep them as they are for now and add 1 to the exponent, divide by the new exponent, and then put u back in before I put my limits of integration on there. So negative square root of 3 over 4. 2 minus 2 is 0 cubed, so blah blah blah, 0. And then put in 0. 2 minus 0 is 2. 2 cubed is 8, so I have 8 thirds. So I have negative square root of 3 over 4 times 8 thirds. So minus and negative gives me plus, that's gone. So I have 8 root 3 over 12, which reduces to, because a 4 can come out of both of them, 2 root 3 over 3. And that's your final volume. Oh wow, only did one example, huh? Let me make sure we don't need any more examples. Should we do that first one? Okay, we kind of did that. I guess we'll just say that's good. I wanted to show you a demo. So before we move on, I'm going to open up a website. All right, never mind. So just you do these problems, page 468, 71, 72, 74, and then on the AP page at the end of chapter 7, do 1, 3, 5, and 9.